So we're on chapter 8 now and dealing with, well, it's mostly limiting reagent concept. And this is one of the more difficult ones in the semester. So, like with intro chemistry, you come every day. You come to class. There's a new mental model, and this one, and some of them are relatively easy. Some are relatively hard. And this is one of them that students find kind of hard, and it's kind of all also brought into theoretical yield and actual yield. So that's what we're going to cover today. So we're going to start with a limiting reagent problem, but it's an obvious one. How many grams of glucose can be synthesized from 58.5 grams of carbon dioxide? So in excess water. So it tells you right away that the carbon dioxide is the limiting reagent. So and reactions, if it's to go to completion, they keep on going until one of the reactants is consumed. And when the reactant is consumed, then the reaction can't progress any further. So this one's gonna keep on going, and also this includes another step that students have a hard time with, is the stoichiometric ratios. So we're trying to start with mass of carbon dioxide, go to mass of glucose. So think about moles. We're going to convert carbon dioxide to moles, and then convert to moles of glucose, and go to mass of glucose. So here are the individual steps, and there's a new one here, and it's converting between moles of carbon dioxide and moles of glucose. And you do that by using the balanced chemical equation. So that middle step is usually where students have that hardest time. So let's look at this. So you start with mass of carbon dioxide, change to moles of carbon dioxide. Now the next step here, and you get this from the balanced chemical equation, and this is typically where, like I said, where the students have the hardest time, is converting between moles of glucose, moles of, it doesn't matter what it is, it's just a different species, right? Moles of product, it could be another reactant. It just depends on what the problem calls for. But you get this from the balanced chemical equation. If you do not balance the chemical equation right, you will have the wrong ratio and you'll get the wrong answer. So now we convert between moles of carbon dioxide and moles of glucose, the tough step, and then finally a molecular weight of glucose, and we get about 40 grams. So, okay. Now let's look at another one here. So when this is a hydrolysis of NO2, reacts oxygen and water according to the simplified equation, NO2 plus oxygen plus 2 waters makes 4 nitric acids. So assuming that there is an abundance of oxygen and water, how much nitric acids in kilograms forms 1,500 kilograms of nitrogen dioxide pollutant. Forms from that amount of that many kilograms of NO2 pollutant. Okay, so limiting reagent problem, but we're excess everything else. So we're gonna start with the mass of NO2, and then we gotta find the mass of nitric acid. So we're gonna obviously convert to moles and convert to moles again from between NO2 and nitric, and then from moles of nitric we can get mass of nitric. And the thing is, to start off in kilograms, so pay attention to the units. So pay attention to the units as you go through this. There is a way you can do this, and you might see it in other places. You can use something called a kilogram mole. So when you say a mole, you usually mean a gram mole, and that's what Avogadro was going for with this number. But you can have other units. You can have a pound mole, for instance, but a kilogram mole is a little easier. It's so it's 6.2 times 10 to the 26 instead of 10 to the 23rd. So it's one of the ways to get around that. But you can, I mean, why not just stick with gram moles? Well, I don't want to confuse you too much, but if you see these units in other places, you kind of know now where they come from. It's just the Avogadro's number changes and when you do it. So with the relationships here, at least it's a 1-to-1 molar ratio, but it makes sense though because nitrogen is the only one species in both. And there's the mass of NO2 and the mass of nitric acid. And let's go ahead and do this. So we start off with mass of NO2, convert to grams. Then we convert to moles of NO2. Now we go between moles of nitric and moles of nitrogen dioxide. Now we go then into moles we go from moles of nitric to grams of nitric, and then we go for kilograms. So this forms 2,100 kilograms of nitric acid. Does it make sense? Yeah, it makes sense because nitric is also a little more massive than NO2. So right, so it makes sense. It's going to be a little bit more, but it's on the same order. So yeah, in my mind, this makes sense. So let's look at this reaction. 2 aluminums plus 3 chlorines makes 2 aluminum trichlorides. You begin with 0.552 moles of aluminum and 0.887 moles of chlorine. One is the eliminating reagent and the theoretical yield of aluminum trichloride in moles. So from this, just glancing at it, we don't know which one is the eliminating reagent. We have to calculate it out. And so we're going to calculate it out to see what amount of aluminum trichloride we get for both. And now you have to pick the smallest one. So we can do this. So pick the smallest one, and then with the starting out with the 0.552 moles of aluminum and 2-to-2 molar ratio, and we get 0.552 moles. And then starting off with the moles of chlorine, and then the 2-to-3 molar ratio, and you get this from the balance equation. Tough step. That's a tough step for students in following. And you get slightly more, and we have to pick the answer that's slightly less. So, one of the reasons why is if you pick the one that's more, you break the conservation of mass. And this one is not as apparent, but the next we talk about ammonia synthesis, it'll make more sense. So now, as promised, ammonia synthesis. So you can synthesize ammonia this way. This is not typically how we synthesize ammonia, but we'll make it in this way. And in the imaginary world of academia, we usually make ammonia over an iron catalyst using hydrogen and nitrogen. So not in the gas phase. Okay. So what's the maximum amount of ammonia in gram can be synthesized from 45.8 grams of nitrogen monoxide and 12.4 grams of hydrogen? And looking at it, I probably would think it's the NO, because that's going to be about not like 2 moles of NO, and then the hydrogen's going to be so it'll be like 6 moles. So it's a tough one though, because of 2-to-5 molar ratio. We'll see. But okay, so we got these two here. That's a molecular weight of nitrogen monoxide and hydrogen. And so we have to do the eliminating reagent, and we pick the one that's lowest. Okay. So, and this is the way you go. You start off with the mass of the reactant, to the mole of the reactant, to the mole of the product, and then the mass of the product. And then we have to pick the one that's the smallest. So here's some of the relationships that are used and the molecular weight of these. So hydrogen is 2, ammonia is 17. And let's go ahead and do this. And when it reacts, reacting all the way, starting with the 45.8 grams of nitrogen monoxide, reacting on down, and then you get 26 grams of ammonia using the nitrogen monoxide, and then with the hydrogen, you get 41.8 grams. So I'm going to back up a little bit. So remember there, about 42 grams, and then let's look at the equation at the start. And you're going to get the same number of moles of water, and water is heavier, right? So water is 18, ammonia is 17. So in the chemical reaction, and so if we're getting about 45 grams of ammonia in this, which means we're going to get about 50 grams of water, which means we're going to get on the order of 90 grams of product if that's the case. And if you look at what you start off with so 46 and 12, right? So that's 58 grams, and so you start off with 58 grams of material, and if you're generating over 80, close to 90, that's a brick in the conservation of mass. So that's one of the checks you can do. Is if I mean, obviously with the bottom one starting the hydrogen, you're getting more matter at the end of your answer, and matter is not created. I mean, at least, I mean, it can be with energy, yes, I know, but I mean, in a typical chemical reaction, the law of conservation of mass holds. So that's another thing. If you pick one and then you're like, well, why can't it be that way? Well, because of the law of conservation of matter. And that's also, so you have to pick the ones to less. So because then that's the only one that's gonna make sure that the law of conservation of matter is in fact upheld. So let's go through one with theoretical yield and percent yield. So copper 1 oxide reacting with carbon to form 2 coppers and carbon monoxide. So we have 11.5 grams of carbon reacts with 114.5 grams of copper oxide, and 87.4 grams of copper are obtained. Determine limiting reagent, theoretical yield, and the percent yield. So, okay, we have the amount that we start off with, and then they produce. So we're going to figure out what the limiting reagent is, and then how much we should have. That's the theoretical yield. And then take the actual yield divided by the theoretical yield, and we get the percent yield. So similar setup for all these. The mass of the reactants goes to the moles of the reactants, to the moles of the products, and then the mass of the products. And then we pick the one that's the lowest. And so let's go ahead and do this. Oh, have we done this? Here we go. So doing this, we react and we find out that copper oxide is the limiting reagent, and because it's the lowest, right? So as we illustrated before, if you pick the other one, you're going to break the conservation of mass. So that's the lowest. And let's do the actual yield, or the percent yield. So what we should get is 101.7, and what we actually get is 87.4, and that means we're 85.9% yield. So, okay. So let's talk about this and what it means. So first of all, a lot of students are like, why don't we get 100% every time? Well, there's a couple reasons. The reactants can be impure. So, I mean, especially for ores, like when and this is how we get metals. We get metals by taking ore and cracking it with carbon. This is one of the most common ways to get metal. And, I mean, there are some metals we get in other ways. So, I mean, like aluminum, we use electricity, and gold. We sometimes use a lot of things like either mercury, which we shouldn't, or things like cyanide to leach them. But for most metals, we get it by reduction of carbon. And so just, throw the ore, throw the carbon and some lime in a blast furnace and heat the heck out of it. And then the molten metal comes out and the slag floats up on the top. So this is how we get our most of our metals. And the ore is probably not pure, right? So it's not going to be amazing analytical grade. So, I mean, actually 80% is pretty good if you think the stuff you're digging up from the ground. It's going to have other things too in it, like slag. Slag is typically calcium, magnesium silicates, and it usually floats at the top of molten metal. So if you wonder, or you heard the term slag before. The other thing is the limiting reagent here we find out is the copper. The copper oxide, the copper ore is limiting reagent, and this is what it should be. So imagine that you're running this plant, you're a chemical engineer, and you're running this plant. I mean, I know it's going to be a lot bigger than 11.5 grams. It'll be like 11,000 tons instead of grams. But say you're you're running this plant and you have this situation, uh, you it's like, and if the boss walks by and say, hey, what you doing, what's going on here, if this is the boss looking in, the boss should give the engineer a big promotion, a big raise, say you're doing an amazing job. Why? Because carbon is cheap and ore is expensive. And if you want to have something that you pick the limiting reagent for, you should pick the one that's expensive, right? So, and maybe the engineer could use a little bit, because he's probably think a little wishful if you look at the amount here, that it is quite a bit higher. If with the carbon, maybe you could put a little less carbon, but still, it's not too bad. It's different by 20%, so by a fifth. So I mean, if it was off by like 300%, you're like, oh, I don't know, that might be a little too much carbon you're throwing in there. But it's close, but it's also enough to make sure that every single copper atom that's available, we're getting out of that ore. So that's a good engineer right there. So, and I hope giving the context to this and where it works in society. So hopefully it helps you understand this problem more. So this is a pretty real problem. I like this one. Okay, so now we're going to move on and talk about stoichiometry and involving heat of reaction. So we haven't talked too much about enthalpy, and enthalpy is the amount of energy that can be released under constant pressure. So what does that mean? It's also path independence, and what does that mean? So it scales directly with the chemical reactions and the amounts. So so let's say you burn a gallon of gasoline, you get so much energy out of it. It makes sense then if you burn 2 gallons of gasoline, you get twice as much energy, and if you burn a half a gallon, you get half as much. So energy scales with the amounts. And of course, when we write chemical reactions, we put the heat of reaction there in terms of the heat of reaction and like the per like moles of a reaction as written. So when you see this propane reacting with 5 oxygens to form 3 carbon dioxides and 4 waters, and the heat of reaction is exothermic, negative 2044 kilojoules, and it's per mole reaction. So, and it's as written. So we want to figure out if you have the home barbecue has 11.8 kilograms of propane. How much heat in kilojoules if we burn it all? Okay, so let's burn it all and maybe grill some tasty steaks while we're at it. And how do we do this? Well, we have to look at the molar ratio between the reaction and the propane, and then scale it that way. And if you look at the balanced chemical equation here, so for every 1 mole of propane, you have the full 2044 kilojoules of energy from that. So just like when you're converting between reactants and products and stoichiometric ratios, that's how you do it with this. If it was oxygen, for instance, you'd have to divide for moles of oxygen, you have to divide it by 5, because it's 2044 kilojoules per 5 moles of oxygen, for instance. But we're not looking at oxygen, we're looking at propane. So we have the propane. We're going to figure out the mass of propane. Then we get the moles of propane, and then we'll get the energy. So and that's exactly what we do right here. So start off with the 11.8 kilograms. Convert that to moles of propane, and then the straight shot there, negative 2044 kilojoules per mole propane, and we get negative 5.47 times 10 to the 5 kilojoules. That's a lot of heat. That's a lot of tasty food you can make on your barbecue with all that heat, right? So, and we're at the end of this problem set. So, hope this helps.